Okay, so there's an important idea. It's called the reaction half-life. It's important because it allows us to quickly estimate like what concentrations will be later, but it also actually helps us to figure out what the reaction order is by really not doing anything other than observing and looking at what the half-life does on a graph of concentration versus time. So half-life is the time, so not to be confused with the concentration, but half-life is the time that it takes for the concentration to reach 1/2 of a value. Okay, so for example, if I have a graph like this, right, and it goes like this, right, well, how long does it take to go from here to half of that value? So you're actually going on the y-axis and cutting across. And so your half-life will be this time interval that's right here. Okay. Now, that would be a zero order, right? If you remember, this is concentration. This is time on this axis. Now, the usual symbol for half-life is T1/2. And these graphs all look different for different orders of reactions. Now, you've seen a first order already. I showed you that one earlier, and that's what I've drawn here. So we're going to look at the first order reaction. Okay, so I showed you zero order, I should say already. So we're going to do a first order now. And the half-life can be used to determine the rate constant, and the half-life trend can use to be determined the order. So the equations for determining the rate constants are come directly from the rate laws. So let me just show you some data first. Okay, so this is our first order data, and this initial concentration is 0.0165 moles per liter, so molarity units, right? So when we go from here and we go halfway down, right, that point there. So I went from this point here to this point here. That's half of this value, right? The half-life for that is this time here. Now, it's roughly around 1400 seconds. I'm not going to get too detailed in here, but T1/2, right? Approximately 1400 seconds. Maybe a little higher, but it's pretty close. Trying to eyeball it because it's not zoomed in here. Now, here's the important thing. When we're looking at half-life trends, the changes in half-life for the different orders are really big. So we're going to try to eyeball what the next half-life is, okay? So when you're doing the next half-life, what you need to do, and I'm going to use a different color pen here. What you need to do is say, okay, what if this was my initial concentration, right? I want to go to half that concentration. So that's now this, right? Now it's this dashed line is supposed to be that half-life or half-life concentration. It's just half of where it started again, right? So half of this and then half of this. The time is this interval here, which is marked out here. And it's about 1400 seconds. So T1/2 is about 1400 seconds. It might be a little longer, might be a little lower, but it's pretty close to that. Well, let's look at the third half-life, right? And the third half-life, what we have is, again, where do we start? We're going to get a different color. I'm starting here, right? And I'm going to half of that value that's here. And then, right, what's the time it takes to get there? And that's here. Like this. So that's my half-life for that part of the data right now. So T1/2, again, what is it? Well, it's about 1400 seconds. So this pattern, right, is what we know to be the behavior for first order reactions. For a first order reaction, the half-life, the T1/2, is constant, is what they say. Now the concentration is not constant, right? It's constantly going down is what it's doing, but T1/2 is a constant. It takes the same amount of time to reach every half-life, right? And this, again, is very different than zero order or second order, okay? So, what do the equations look like that allow us to calculate? If we assume, right, T1/2 is around 1400 seconds, and it looks like it's first order because I just said this, right? How do I calculate the rate constant? So let's look at that next. So I want you to learn this math trick, right? And what the math trick is half-life. The concentration at time t, right, is 1/2 the concentration that you started at, A0. So if I know that that's true, then what I can do, right, is I can plug that into the equation. I can do a substitution. And the neat thing happens. It looks like this, okay? It goes ln 1/2 A0 divided by A0 is equal to minus KT. So what does that mean? It means the A0s will cancel out, right? And what it's telling us, right, the concentration goes away, right? It's telling us the half-life doesn't depend on the concentration. And also it does this. It tells us that natural log, right, of 1/2 is equal to minus KT 1/2. So this is T 1/2 like that. Because, right, that's the concentration at half when it reaches half. So that means that must be the time that it reaches half. So now this is T 1/2. Most of the time this rearranges. Now you notice there's a negative here. And so I'm going to bring the negative over. This is going to be, KT 1/2 is equal to natural log of 2. And that's what I actually have written down here. I almost always just remember natural log of 2, and then I always have to relearn this number every time. I always forget like which number it is. And it doesn't have units, by the way. Okay, so from the data that we had before, right, we said T 1/2. From just the previous graph, T 1/2 is around 1400 seconds, right? So we want to figure out what the rate constant is. So I can rearrange this equation. I can say K is equal to 0.6931. That is 4 sig figs, by the way, over, right, T 1/2. Like that. So I can pull out my calculator. Let's see here. I've got something in front of it I got to move. You can't see it on the screen though. Get my calculator out. And I'm going to go 0.6931 divided by 1400. And that comes out to be 4.95 times 10 to the minus 4. Okay, so 4.95 times 10 to the minus 4, and the units are 1 over seconds. Those are the first units for a first order rate constant. Rounding, I really only have 2 sig figs, so this is one of those weird ones. This will be 5.0 times 10 to the minus 4 on rounding. Okay, so why is this thing important, right? Just again, you can determine K from experimental data very quickly using this method. And you can also determine whether or not it's first order, because what the first order half-life does is it stays the same for every half-life, right? So it's a quick way to use a graph to figure out the half-life. The order. And it's also a quick way to graph data, since you know for first order reaction, the concentration, right, is half for every half-life. So let's say I know the half-life is 6 seconds, right? And then let's say you start with 0.8 molar, like this. I'm going to go 6 seconds, 12 seconds, 18 seconds. And I want to know the general shape of the curve. Well, after the first half-life, it'll be here. After the second half-life, it'll be here. And after the third half-life, it'll be here. So the graph kind of goes like that, right? And I would do a neater job if it really mattered. But that's how you do it. And over here, I would have molarity. And down here, I would have seconds. And I'm just graphing it based on the half-life. Okay. The last reason that you need to know this is this kind of stuff comes up on the test all the time. And here's why it's important. There are many ways to do these problems. This is the fastest way. And so if you can do that, right, instead of doing the longest way or the hardest way, you'll be more accurate in your calculations and you'll save yourself a lot of time. So I'll demonstrate that with this problem, right? It says starting with 0.200 molar dinitrogen pentoxide, how long does it take this first order reaction to reach 0.5 molar, right? K is 4.8 times 10 to the minus fourth per second. All right, so how do you do this, right? So this is what you do. You say, okay, oh look, we're going to do the half-life method, right? This and this are related to each other, right? Because if I go from 0.2 to 0.1, that's one half-life. If I go from 0.1 to 0.05, that's a second half-life. So really what I'm looking at is two half-lives. The hyphen doesn't need to be there. So what I'm going to do is calculate the half-life using a rate constant, right? So I know K, T, 1/2 is equal to, and this is always what I remembered, but you can remember the 0.69, whatever it is, natural log of 2, like this, right? And then I know T 1/2 will be equal to ln of 2 over K, and then I'm just going to plug that in. It's 4.8 times 10 to the minus 4 seconds. So it's going to be ln of 2 divided by 4.80 times 10 to the minus 4th seconds. And grab my calculator, right? And then I'm going to go 2, and then I'm going to do natural log right here. So then that's the number, right? I just use this button that's down here. And then I'm going to say divided by, and then 4.8. And, you know, if I hadn't been talking this whole time, I'd already been done. Right, so E for change sign. It's 1,444 seconds, right? Now, two half-lives would be what? It would be twice that, right? So that would be equal to, so the time it takes to reach 0.5 molar is 1,444 seconds. That's T 1/2 times 2, so that'll give me 2,888 seconds. Now, read the question, right? Because this is another place people get stuck. What does it have to be in units of? It's looking for minutes, not for seconds, because, well, that's just a big number. So we're going to go like this, right? There's 60 seconds in 1 minute. So go back to my calculator. I didn't do anything yet, so what I'm going to do is times 2, and I'm going to divide it by 60, and that comes 48 minutes. Probably 48.1 minutes. Let's see some. No, it's 2 sig figs, so 48 minutes. It comes out like this, and then it has 2 sig figs here, so I'm just going to go like this, 48 minutes. All right. That's the fast way. And again, if I hadn't talked about it, I said, oh, I just need to set the equation up and calculate it. That's what I would have done. Okay, so we'll do the integrated rate law approach. And to do that, we have to figure out which equation we want to use first, right? So we're trying to figure out how long it takes. Remember, there's that whole list of equations. I want the one that is easiest to find the time in. And that equation will be, of course, the one that gives me most directly time. So it'll be natural log of AT over A0, right, is equal to minus KT. And then I'm looking for that. So what I'm going to do is rearrange the equation. So I'll have T is equal to, right, natural log of AT over A0 divided by minus K, like that. Now, what I'm going to do is find the values I need and plug it into the equation. I'll write that down over here because that's where all my space is. So T, the time it takes, right, is going to be equal to natural log of, and that's 0.05 molar, right, 0.050 molar divided by 0.200 molar, like that, divided by negative, and then 4.8 times 10 to the fourth. Seconds to the minus 1. Now, this is per second, right? So it's 1 over seconds. And so the unit for this will end up being seconds. The units up here cancel. Okay, so let's simplify this a little bit. Okay, so we're going to go, this is natural log of 0.25. Do that bit first. And that's still the same, minus 4.8 times 10 to the minus 4 seconds to the minus 1. Let me plug that into a calculator. That's just less work for the calculator and hopefully more work that works. Okay. So I need to go this. It's 0.25, and then I'm going to do natural log like that. Okay, so negative 1.386. If you wanted to write that down, you could. Divided by 4.8 times 10 to the 4. I need to change the sign, and I'll change that sign as well. Change sign, where to go? Here, yeah. So 2888. 2888 seconds. Now look at this, right? Go back. That's what we got here, right? Same answer. But if you'd done the half-life and you knew it was first order, you would have just calculated that almost directly and then just multiplied by 2. Here was a lot more calculator intensive work, and it's easy to make a mistake. In fact, I will confess, I went through this whole thing once and I got the wrong answer, and I thought, what did I do wrong? And then I had to go back, and I had typed numbers in wrong in the calculator because, you know, when you're doing the logs and dividing and all that kind of stuff, I screwed something up. Anyways, that will again come out to be, right, same amount of time, 48 minutes, because it's the same time. So this will be 48 minutes. Okay, so those are kind of the two approaches. One way is to just, if you know the half-life and it looks like it fits a half-life, pick that. Now, had this number, this 0.5, not been an even half-life, then you would have had to do this. So you actually have to know both. But sometimes when we put questions on tests, part of it is a time thing, right? You need to manage your time and you need to find the fastest way. So think about how you're going to do the problem before you actually do it. Now, hang on. Okay, so here's some data. It's actually second order data. So let's go through our little analysis, right? Let's see what happens to the half-life in second order data. So it's starting up here. See, zeros, it's not like the graphs I had before. So 0 is here. So here's the concentration. It's 0.1 molar, right? So that means in order to get to the first half-life, right, it has to go to 0.05 molar. So that would be here. Now normally I would use a ruler, right? But I'm just going to use this. I'll freehand it like that. And then we'll try to estimate what this is. And it's pretty close to 20 seconds, right? So the first T1 half, right, is approximately 20 seconds, right? Okay, so let's get a different color, and we'll do the second half-life. And in fact, this would be a good time for you to pause the video, and then I'm going to mark it out, the second half-life, to make sure you can pick it, and we'll compare the first and the second half-lives that we get, okay? So pause the video, and then it'll pop up on the screen magically. Okay, so that's what I did, right? Hopefully you got something like that. This is 0.5 here. And this is point, so 0.05. This is 0.025 here because this is 0.03. You notice this is actually not going to 0, so if the graph looked funny to you, that's why it looked funny to you. 0 is like, I think, down here somewhere, right? So let's see here. What does this look like? Well, that looks like 20 seconds. The second half-life, and this is a common mistake, is not 60 seconds. It's based on where you started from here, okay? So the first half-life was 20 seconds from when it started. The second half-life is 40 seconds. And what you'll notice is that T1 half, right, is approximately 40 seconds. It doubled. Now, remember, think about this is a second order reaction, and we talked about this. In a second order reaction, the exponent in the concentration is squared, and it will have a bigger effect as the concentration goes down. So the result is, instead of taking 20 seconds to get to the next half-life, like it does in a first order, it took twice as long, okay? And the next half-life would be what, right? It would be 80 seconds. Okay, so if you were thinking like, when does the third half-life happen? This is something to think through. The first one happens after 20 seconds, right? The second one happens after 40 seconds. The third one happens after 80 seconds. But that's 80 seconds more. So the total time is 20 plus 40. That's 60 plus 80, right? It's 140 seconds. So it's one of the things to keep track of that's a little bit tricky with half-lives is when you're trying to predict what the time is later and you're thinking in terms of half-lives, you got to make sure you're adding them all together properly, okay? Well, what does the equation look like that gives us this, right? Well, in the half-life in a second order reaction, this is the second order reaction, can be derived the same way by making that substitution of AT is equal to 1/2 A0. Now, what I'm going to do real quick is sort of show you how that works out. But that means this, right? This is 1/2 A0. So this is going to be 1 over 1/2 A0. That's equal to KT. I don't have my T there, got short. Plus 1 over A0. This will actually become 2 over A0. And then I'm going to subtract 1 over A0 from it, and that gives me KT. And unlike the first order and the zero order reactions, there's not a negative sign in front of the K, it's just a positive value, right? And so, this is now T1 half, right? Because it's the half-life concentration, so that's the half-life time. Is going to be equal to 1 over A0 is equal to KT1 half. Now, thinking about what we were saying, the half-life doubling, right? What happens is this equation will rearrange to T1 half is equal to 1 over A0 times K. And I actually put this down here to check myself, but that's what it is. So you have an initial concentration, right? And that gives you a half-life. But when this, right, is half of that concentration, that's your next half-life calculation, then T1 half will be twice because that concentration is now half, right? And it's in the denominator. All right. So hopefully that made sense to you for second order reactions. So here's a quick calculation you could do then, right? It says a second order reaction has a rate constant of 0.25 molarity units per molarity per second, right? So that's the K. At a concentration of 0.1 molar. How long in seconds does it take the concentration to reach 0.025 molarity units? Again, there's two ways to do this calculation. The quick way would just be to calculate the half-life. Okay, so I'm going to do the half-life method. I'm going to say T1 half is equal to 1 over 0.100 molarity units times 0.25 molarity to the -1 seconds to the -1. So let me get that on my calculator. So it's going to be, I'm going to do the math at the bottom first, 0.1 times 0.25, and I'm going to invert it. So do the inverse, equals, and I'll do the inverse. Where's my inverse button? Here. So that first half-life is 40 seconds. And the way the units work again is the molarities will cancel because that molarity is on the bottom. This is 1 over seconds, so it's 1 over 1 over seconds, so it gives me seconds as my unit. My sig figs is 2, so I'll just do that. So how long does it take, right, for it to reach 0.25 molar? Well, this is the starting, this is the final. You'll notice that that's 2 half-lives. And, you know, at first this may seem foreign to you, but you get used to seeing it, and it becomes like a trigger. Like if it's exactly a quarter, then you know, like, oh, that's 2 half-lives. Or it's an eighth, that's going to be 3 half-lives, that kind of thing. So now what I'm going to do is do this. I'm going to do this one out on the slide like this for you. The first one's 40 seconds. It's a second order reaction. The second one's 80 seconds. So the total is 120 seconds, like that. All right. The other way to do it is to take all the values and plug them into the equation like we did earlier. Actually, we did this kind of problem earlier where we plugged numbers in to get a concentration. But in this case, we'd be doing it for time, okay? Okay, so this is the summary of the half-life stuff, right? First order, the half-life is constant, right? And we can calculate it from an equation that says ln of 2 is equal to k times t1 half. The second order doubles for each half-life, and again, we can calculate that from equation that's up here, actually. I wrote it and then, sorry, I should have just let the slide do it, but it's more fun to write it. T1 half is equal to 1 over A 0 times K, like that, okay? Now, I didn't say this for zero order, okay, but the zero order equation looks like this. It's going to be T1 half, and it says C text here because I don't want to take the time to do all of these like this, is equal to A 0 over K 2K, like this. Okay, so the thing about, and I just want to show you what this looks like, so you understand. I'm not going to spend a lot of time on it. It looks like this, right? A zero order reaction looks like this. So if this is my initial concentration, let's say that's, let's just say it's 1. That'll be an easy number to deal with. Then when I get to a half, right? This is my first half-life. This is my T1 half. Now remember, in a zero order reaction, the rate doesn't change with concentration. So if I make the concentration twice as much, it'll take twice as long. That's why this term is here like that, right? Now, here's the thing that's interesting about it. The second half-life, the time to get to 0.25, right? That's going to come here. And not a great job of spacing it out. But here's the general trend. It becomes 1/2 of the original one. So the half-lives for a zero order, because the slope doesn't change, is going to get shorter and shorter and shorter until you get to 0. Okay. Again, all of these can be used for determining the graphing, and looking at half-lives can be used for determining whether or not it's 0, first, or second order by looking at successive half-lives and seeing how they change. It can be used for quickly calculating, once you determine the order, quickly calculating the rate constant. And it can also be used for predicting concentrations in the future, provided that they're at half-life intervals, right? The time is at half-life intervals. and it can be used to do things like that. So there's a lot of uses for this. So it seems like kind of at first like it's a weird little side thing, but it becomes very useful as you study kinetics.